Welcome to Chapter 1, which introduces the fascinating world of smart materials. Smart materials are engineered systems that respond adaptively to external stimuli. Unlike passive materials, they alter their intrinsic properties in a reproducible, controllable way. The spectrum of smart behavior maps material classes to their input stimuli and output responses. Examples include piezoelectric materials responding to mechanical stress with an electric charge, and shape memory alloys using temperature to recover shape. A smart material shows a significant, reproducible change in macroscopic properties from an external stimulus, enabling sensing, actuation, energy conversion, or adaptive functions. This behavior involves coupled physical effects, like mechanical, electrical, and thermal responses. Piezoelectric materials generate voltage when stressed, the direct effect, and conversely, applying voltage creates stress and deformation, the inverse effect or actuator. Real-world smart materials rely on nonlinear effects like hysteresis, which provides a memory to the system. This involves switching states, transforming crystals, or absorbing heat. Shape memory alloys and polymers allow for large deformation that can be recovered through changes in temperature or stress. This shape memory effect results from a martensitic phase change, or induced elasticity. Smart behaviors are described by constitutive equations, which define relationships between generalized, quote, forces and responses across mechanical, electrical, magnetic, thermal, and chemical domains. Macroscopic smart behavior originates at the lattice level from symmetry breaking and atomic rearrangement. This includes polarization in piezoelectrics, phase change in shape memory alloys, and microcapsule release in self-healing materials. Smart properties are often induced during post-processing through steps like poling for ceramics, training for shape memory alloys, and curing for polymers. Performance is verified using various tools: XRD and SEM for structure, Sawyer Tower circuits for ferroelectrics, DSC for phase transitions, VSM for magnetic properties, and tensile testers for mechanical response. Applications include sensing using the direct effect, actuation with high precision using the inverse effect, and artificial muscles made from electroactive polymers. Electroactive polymers, or EAPs, are materials that change their volume when a voltage or electric field is applied to them. Smart materials enable autonomous function in biological and energy systems, such as nitinol stents in biomedicine, piezo cantilevers for energy harvesting, and phase change materials for thermal storage. Reliability challenges include fatigue, aging, and hysteresis. Engineering solutions involve doping, composite toughening, and encapsulation to manage these limits of intelligence. Modeling and simulation predict behavior across scales, from finite element analysis for device geometry down to density functional theory for calculating atomic energy barriers. The future of smart materials is soft, printed, and integrated, featuring programmable matter via 4D printing, wearable biosensors, and ferroelectric memory for AI. The evolution of smart materials is defined by a stimuli-response capability governed by coupled field physics and phase transitions, with applications in sensing, actuation, and energy. We now explore the evolution of intelligent structures by comparing high-performance materials versus smart materials. High-performance materials are passive, designed for static resistance and load capacity, and do not adapt. Smart materials are active systems that function as sensors and actuators, reacting to external stimuli with reproducible physical changes. This video will explore high-performance materials and smart materials, focusing on the physics of strength and responsiveness. High-performance materials utilize dislocation glide mechanisms, including solid solution hardening, grain boundary strengthening, and precipitation strengthening, to enhance strength. A key example is nickel-based superalloys, the pinnacle of metallurgy, used in aerospace jet engines. Their strength comes from a face-centered cubic matrix fortified by intermetallic precipitates, allowing operation at extreme temperatures. Advanced polymers and ceramics also showcase high performance. Ultra-high molecular weight polyethylene delivers impact dissipation for biomedical joints. Silicon carbide is a robust ceramic with high thermal conductivity. CPEAK and zirconium oxide form hybrid biocomposites with matching elasticity to human bone. Carbon fiber reinforced polymers, or CFRPs, are another high-performance standard. They are roughly 1/5 the density of structural steel, but provide nearly 10 times the longitudinal tensile strength. However, Their mechanical anisotropy means they rely on the weaker epoxy matrix to resist compressive forces. Moving to smart materials, their intelligence quotient is based on responsiveness and agility. They fall into two categories: energy-exchanging materials like piezoelectrics and shape memory alloys, and property-changing materials such as magnetorheological fluids and electrochromics. Shape memory alloys demonstrate the shape memory effect and superelasticity. This involves a cycle between the austenite parent phase and twinned martensite, driven by temperature and stress changes, allowing them to recover a programmed shape or instantly recover after unloading. Rheological and chromic smart materials include magnetorheological fluids, where a magnetic field aligns ferromagnetic particles, transitioning the fluid to a semisolid. Electrochromic glass uses voltage to alter optical transmittance via ion intercalation within a metal oxide layer. Comparing the two paradigms, high-performance materials aim for static maximization of strength. Smart materials prioritize dynamic adaptation to external stimuli. While HPMs offer high resilience, SMS leverage physical instabilities to generate functional responses, but require system integration. The synergy between these material types can be seen in intelligent structures and structural health monitoring. Embedding smart sensors like PZT or FBG into composites detects damage. However, this embedding can disrupt fiber alignment, causing significant reductions in shear strength and stiffness. Autonomic self-healing composites overcome damage autonomously. Extrinsic systems use microcapsules with reactive healing agents that rupture upon cracking. Intrinsic systems utilize thermoplastic chains that diffuse and entangle when friction-induced heat transitions the polymer. In engineering case studies, modern high-rise seismic mitigation uses smart Mr. fluid dampers with semi-active control to dynamically detune the building. For long-span bridges, continuous SHM via embedded sensors executes operational modal analysis, pinpointing fatigue cracking decades before failure. The future of engineering lies in the multi-material frontier, the seamless integration of high-strength composites with smart components like sensors, fluid dampers, and self-healing networks. This will make fully autonomous, self-diagnosing, and self-repairing structures the standard.